So when do we use what? During the start of these topics, I did discuss about why and when we have to use each of these things, right? Like say, suppose Monte Carlo. When can we use Monte Carlo? Let's make it a discussion. When do you think we can use Monte Carlo?
Like for all of them, we don't have a model, right?
Yes, we don't have a model, but
honestly, like it is quite vague to me. Like yeah, I can't like and we have compared like so far we compared Monte Carlo against SARSA, right?
Against TD learning, yes. SARSA is a
yeah, actually I wanted to get to that because we didn't like if you remember, like TD is important because
yes.
At heart SARSA is temporal difference, right?
Yes. Okay, so I was going to teach about this, but I'll do it now anyways. You have model-free reinforcement learning. Okay, reinforcement learning classified as model-based and then model-free. So in model-free, you have many, but let's focus on this one: Monte Carlo and TD. Okay, then within TD, you again have many, but let's focus on SARSA and Q-Learning. Okay, within this, you will have many, and one of them is called reinforce. We'll be studying about that in the coming lectures. Okay. What we are doing in TD and MC is computing the, okay, there is one more classification here, and that is value-based. Or else let me simply show a slide that I did. I was going to teach it in the next class, but since you asked me, I'll go to it now. Okay. So within reinforcement learning, you have classifications as model-free and model-based. Because we are focusing primarily on model-free, I just zoomed into that part of the taxonomy here. So within model-free, you again have different classes of algorithms. Okay, you have value-based, you have policy gradient, you have actor critique. The later two will be studying in the following lectures in the coming weeks. Okay. Within value-based, you again have two classifications: Monte Carlo, TD learning. Okay, why value-based? What value-based? I'll come to it. I don't want to rush it now. Within this, these two value-based functions, from the name you understand that it has to do something with the value. Okay, and what is the value that we compute here? State value function, and action value function. These are the two value functions we compute, right? So TD and Monte Carlo does both the same thing. Okay, compute the value functions, right? These compute the V stars, the V pi's. Okay, the state value function, that is. Okay. However, if you have to derive the optimal policy from those value functions, state value functions, you first have an intermediate step where you have to compute the action value function, which is the Q stars. So V star, you compute Q star, then you obtain or derive the pi stars from that. Okay. TD and Monte Carlo stops at V stars. Okay, they are methods of computing these value functions. Okay, because at that point in the computation cycle, we are not worried about the actions. Okay, we are simply trying to compute the state value, the state value of every function. Yes, the action comes into play. How? Because we are taking the max over all the possible actions that we can take in that state, but we do not map the exact action to that state and the value. That because is done through the action value function. So here when you are computing the value function, we simply are obtaining how good that state is, that's it. Okay, when we assume that we take the best action in that state, and we don't know that best action. That best action is known through the Q value functions. Okay. SARSA and Q-Learning, and similarly reinforce, algorithm called reinforce and Monte Carlo, helps us compute this thing. By this thing I mean compute the Q star, which in turn gives us the pi stars. Get it? This is how the flow is. Okay. Now when to use what? Why did we use when did we use Monte Carlo, or how did we use Monte Carlo rather? For episodic tasks where we could do the complete run, because we don't have any estimates there. What do we have there? We have actual returns, for which you need to run the episode, for which the thing needs to happen, right? When that happens, you know that, okay, this is the reward I got for this action. Cool? However, with TD learning, what did you do? Estimates, right? So you did not need a full rollout of the episodes. You did one step, and then whatever the estimate of the next step is, you took that into account. You did that repeatedly or iteratively over many episodes for many different states and later many different state action pairs to compute the values, right? So now, are you clear about this Monte Carlo and TD learning now, and SARSA and Q-Learning, right? Dynamic programming was a predecessor to this in the sense that you needed a model for that, okay? So the model-free version of dynamic programming are these two. Clear? You needed a model there, you don't need a model here, right? And since you already have a model there is no question of estimates or actual returns there. Why? Because you have the model. You plug in the numbers, you will get the number, right? So there is no returns that you have to wait for or anything. You simply plug in the values. There are mathematical equations, put it in, you get the number, that is your values. That's it. Clear?
I can do a Monte Carlo and TD for model-based DP, right?
Sorry?
Is that what you said? Like, I can apply Monte Carlo and TD for model-based as well if I have a DP. Is that what you said?
No. What I said is Monte Carlo and TD learning by definition are for model-free applications where you don't have a model. The equivalent in model-based reinforcement learning or model-based applications is dynamic programming.
The equivalent?
Yes. It does the same thing, however, with a model. Okay? Clear? And because there is no question of you estimating anything because you already have the equations, there is no division there as Monte Carlo and TD learning. The only difference between Monte Carlo and TD learning is what? Episodic, non-episodic, like as in estimate, non-estimated, right? There, since you have the equations, there's no question of that. Clear? Okay. So I'll go back to Q-Learning now. Yes. Uh-huh. On policy, off policy. SARSA is on policy, okay? By on policy, you remember the numerical problem we did, right? We had an equation there that said Q of S comma A would go to Q of S comma A plus alpha delta, where delta was R plus gamma Q of S. I'll simply write S prime comma A prime minus Q of S comma A. Right? This was your equation for SARSA. Okay? With Q-Learning, everything remains same except for one change. This is delta SARSA, this is delta Q-Learning. R plus gamma are these equations same? Yes. The only difference will be max over the actions, right?
So you compute the Q of the next state and their common state, find their max before applying by this kind of.
Yes. So there you remember we did 3 iterations. We did pi 1, pi 2, pi 3, right? Pi 1 was right comma right, pi 2 was right comma right, pi 3 was right comma left. Okay, when you are doing this, when you are in state A, okay, this was for state A and B. We had 2 states, state A and B, right? When you were in state A, and this value that you were computing, right, based on policy 3, despite Q of B comma R, if I'm not wrong, was 0.75 or something, whereas Q B comma L was 0. Okay, because we never tried it, so the value was the initial value that we had. Now VB, what is VB in this case? 0.75. Why? Because it is max of, basically equation would simply be max of A for Q, right? Here in this case it would be comma 0, which was 0.75. Got it? Clear? Now here, what you will be doing, what you did in that case was during SARSA, when you were in state A, you, for this action, for this state action value function, you took the value of QBL. Why? Because your policy said that in B you're going to take a left, right? However, with Q-Learning, you will not do that. What you will do is, for the next state here, you will have QBR and QBL, and you will take max of these two every time, irrespective of what your policy says. Even if your policy says L, you will take this value if that has a higher value. Clear? Sorry?
So one of them is like policy equation and the other is the value equation. Same concept.
In a sense, yes, but then, yes, okay. You could see it that way because you mean here you're doing multiple steps to reach the improvement and there you're taking the max. Okay, yes, in a sense, yes.
So when do we do on policy? When do we do off?
Okay. When do we use on policy? When do we do off policy? I have a slide in this lecture where I'll be talking about that, but just to give you an overview, it's your choice. You can do anything when you want. You can do like Monte Carlo and TD learning. You can do Monte Carlo whenever you want. You can do TD because both are applicable for the same set of problems that you have. In both, or rather for both, you don't need a model. So say you want to solve a problem based, and okay, even the previous, the predecessor classification, like value-based, policy-based, and actor-critic, even that depends on your choice. That's a choice-based parameter, right? Yes, there are some other nuances to it where you have to consider the problem that you have, the kind of application that you want to do, your sample efficiency, cost, all those things come into factor, true. But then that isn't, at times everything will check. And at that point, it's only your choice which algorithm you choose. Like for example, later on when you will be studying about, say, algorithms like DDPG, SHC, TD3, those are more or less doing the same thing. One is more sample efficient, one has better entropy, better exploration, but eventually, ideally, all of them would converge to the optimal value. So the choice of algorithm depends on you.
But in the literature, it does come across that like Q-learning is basic and more popular. Like the impression is like basic RL it would be Q-learning. Is that right?
That if you have a discrete model, yes, even your choice of algorithms depend on that as well. Say you have continuous action, discrete states, or you have discrete actions and continuous spaces. So then you have, so basically you make a box, you write all the algorithms, you write all the conditions that you want. Then you tick, I have this, I have this, I have this, I have this, I have this. Then you select which is the most suitable one for that. Does it allow me to do all these things? Like say DQN. Deep Q-Learning is a successor of Q-Learning basically with neural networks, okay? That you cannot use if you have continuous action space or you have continuous spaces, action or the state space. Then you will have to use something like DDPG.
Well, what is the difference, action and state space?
If you have continuous action and continuous states, you cannot use DQN because DQN does not support continuous spaces. It supports only discrete spaces.
When we say continuous space, that implies continuous action and states?
Yes. Yes.
And the discrete vice versa, right?
Yes. Yes.
Discrete action and discrete space.
Discrete states, yes. But just to reduce the redundancy, I'm using discrete space. So yes, those kind of parameters or those kind of decisions those kind of, what do you say? Factors are something that influence your decision of choice for the algorithms that you have. Okay? So yes, let's get back to Q. Any questions till this point?
Thank you.
Pleasure. Okay. Yes, let's go back to the lecture now. Of policy, right? Now, so we talked a lot about on policy and off policy, right? So on policy, now you know, now you understand from this, right? If you are using the same policy to update that you are acting on, it is on policy. If you're using a different policy here, because you see the action changes. When the action changes, it simply implies that it's no more the same policy, right? So when your action changes, you're no more updating the same, because here your Q value would be updated by a action which is not part of the current policy. Therefore, it is off policy, okay? In certain applications, off policy is more efficient in terms of samples that you need than on policy, right? Yes.
Then what is the point of the policy here if we are not going to use it?
You mean on policy?
No, on off policy.
To take an action. If you don't have a policy, how can you take an action? Right?
Can we generalize, like, say off policy, generally speaking, is more sample efficient?
That would be too brave a generalization, because these things, yes, on off policy is sample efficient in some cases for some applications. However, there is no generalization that I could state that yes, this is more sample efficient, this is not sample efficient. So yes. Okay. Yes.
So the meaning of the word reinforce is just not the estimates?
No. Okay. No.
It's like later topic.
Yes, it's a later topic. So forget that this word exists here. I don't want to go in loops. I'll talk about it, okay? So yes. So here you see how does the update rule work? You have the max over the next action that you have. Right? That is the primary difference between on policy and off policy. Rather, that's the only difference between on policy and off policy. Okay? So just like on policy, here the delta is same. It's basically yt. Yt is nothing but this big term. This term is yt. Y. The other one is q. So here you have greedy with respect to current q. That's it. Right? Okay. Now I will not talk on this one. I want you to get involved in this one, okay? What is the main difference between SARSA and Q-Learning? Yes? Okay. Okay, what do you mean by on policy and off policy?
Policy means that the agent will follow a specific policy while he's updating the Q value.
Okay.
And policy means that he will not basically follow the same policy.
Right, okay. Anyone else?
I think we'll see could be convergence is a smaller problem faster than the off policy.
For certain small problems, yes. Okay, so clear? So if you are updating your value functions based on the same series of actions that you were defined with or that you started with, then you are following an on policy algorithm. However, if you are not following from the same series of actions that you started with, and rather you take the actions greedily, assuming that you will take a better action or the best action in that state, you are doing something called off policy, right?
Here, the variance part, Q-Learning is more sensitive to max noise.
Okay. Here, what happens is you assume every time that you're taking the best action, the max action, right? However, because while you're iterating it, it is, say, in the first few iterations, you might see that one action will give you a good Q value function, but that might be far from the ideal action. So the change that will happen in the learning episodes between the Q value is drastic. So the variance is higher. You get it? Whereas SARSA, being that following the same policy, the variance will be smaller.
So if we got by chance a max action, like one anomaly or something
Yes.
strange,
Yes.
This will affect as we're taking max action.
Exactly. So your learning curve would be something like this. Right? This is an exaggeration, obviously. You will hopefully not have these kind of learning curves. Off policy. Yes, off policy. Okay?
Can I ask what a good learning curve usually? It's gradual.
Uh, something like this.
So start low, then high, then usually.
Yes, yes. After you reach a certain, this can vary obviously the slope of this, but yes, after a certain episodes or certain number of steps, you must converge. Like the variance should be small, right? But that will not happen in most cases, so that's fine. Okay. Yes.
So that both the SARSA and Q-Learning using top policy, so the convergence to getting to optimal policy, which will be like the possibility first diagram of SARSA or diagram of Q-Learning, both are using on policy.
No, SARSA is using on policy.
No, if we stick to go to the same policy, if we make it like this, not using on policy, if we make it off policy, phenomena then.
I didn't get you again.
For example, if SARSA, if we in place of on policy, if we use off policy,
That will become Q-Learning. That's the only difference between SARSA and Q-Learning. If you update the values of policy in SARSA, it is nothing but Q-Learning. That's the only difference. Back to the numerical example, and in this example, it's the same example that we used in SARSA, okay? I wanted to show the difference, that's why we're using the same example. So you remember we had A, B, terminal, if you take a right, okay? Reward from A to B was 0. From A to A, that is if you are in the same state, reward was minus 0.2. From B to T, the reward is +1. From B to A, the reward is -2. Okay? Your alpha is 0.5, gamma is 1, epsilon is 0.1. Q initialization is 0, implying Q of A comma R, Q of A comma L, Q of B comma R, Q of B comma L, all are 0. Okay? Why don't we have Q of T comma R and T comma L, the terminal states? Exactly, because we don't have any actions in that. Once we go there, the episode terminates. Right? Okay. So for the first episode, let's assume that the policy is R comma R. Okay, that is take right and right in A and B. So first, okay, we'll write the formulas here. I'll write the formulas here. Your Q update would be Q plus alpha delta. Delta is Q minus, oh no, sorry. Q, this is R plus gamma Q of S prime comma A prime max. Minus Q of S comma A. Okay, this is your formula. So for the first episode, when you're computing delta 1, say you are in state A now and taking right. Okay, what is your reward, immediate reward that you get? A to B 0. Discount factor is gamma. The estimated value would be what? 0 minus previous estimate is 0. So 0. Okay, so no. Yes, your delta 1 is 0. So your Q of A comma R would then in that case be plus 0, which is same, 0. No update on this. Q of A, now you're in B, okay? So Q of B comma R is what you have to compute, okay? Your delta 2 would be, the reward that you get for taking right in B is plus 1 plus gamma times your previous estimate of this. Okay, if you take a right, what will be the next state? Terminal. So therefore no reward, 0, minus your previous estimate of QBR is 0. So this total value would be 1. QBR would in turn be 0 plus 0.5 times 1, which would be 0.5. Okay, after the first episode. Now to the second episode. Okay, I'll follow that one exactly. Okay, any choice. Now let's say your epsilon greedy, based on your epsilon greedy, you get a policy right comma left. Okay, so now remember this is Q-Learning, right? So this is off policy. So first Q A comma R.
So based on epsilon, you said I get R and L based on?
Epsilon greedy method. So basically you simply toss a die based with the probability epsilon, you take the greedy action. With probability 1 minus epsilon, you take a random exploratory action. At this stage in the iterations, yes, the what do you say? The exploitation has not yet developed, but let's just say it's randomly right and left. Otherwise, the intuition of epsilon greedy method is, if you say you have reached a certain number of episodes and your Q tables have been populated enough, right? In that case, if you are, now you know already that no, this action is the best action, yet you do not take that in your learning policy. Why? Because you still want to explore the other regions. But how often do you do it? That depends on the epsilon that you're using. Okay? So QAR would be, in this case, right, the reward for moving right is? So delta 3 now, right? Okay. 0 plus gamma is 1. So 1 times QB what? Okay. What do you take here? BL or BR? So you take, okay, you have max. You have QBR, QBL, right? This is what? 0.5. This is 0. Okay. But if it was SARSA, because it was on policy, you had to take this value, right? Here, because it is on policy and it depends on the max of the action, you will take this value to update QAR, despite knowing that you will be taking a left in B. Clear? So here your value would be 0 plus 1 times 0.5 minus old estimate of QAR was 0, right? 0 minus 0. So this is 0.5. Okay? Then your QBL would be here delta 4. The reward for taking a left in B is minus 2 plus gamma of 1. Now the next action is anyways 0 because it's a terminal state, minus your previous estimate is 0. So your final value is minus 2. Okay? Now your QBL would be 0 plus 0.5 times minus 2, which would be minus 1. Okay? So now after 2 iterations, your Q table will look something like this. Okay? What is a Q table? States and actions. Okay? What are the 2 actions you have? Right and left. What are the 2 states you have? A and B. Rather, let me write this with a different color. The 2 actions you have are right and left. States are A comma B. Okay? After 2 episodes, QAR is 0.5. QAL we still haven't explored, so it is stuck at the initial value 0. QBR is 0.5. QBL is minus 1. Right? You do this again and again and again till what point? How do you know it converged? Over from the previous iteration, right? So when that happens, this reaches a certain fixed value, right? When that is done, this table is populated, right? And it is converged. So the values will not change at that point. Then all you have to do is, how do you make your policy, or how do you extract your policy from that is, like A this, B this, C this. You simply go through this row, you select you see what's the maximum value, and you're like, I'll take action corresponding to that. Remember, it was arg max of A. Therefore, so the first index term here, which is right. So if in A, take right. If in B, take right. This together stitched will form you the optimal policy. Okay? Yes. Sure.
So like, if you start to look deeper, like, you already said that Y is R and L.
Yes.
Yet when I did, because it's off policy, I actually, right was the better one, and I went with it in the calculus for delta, right?
Yes.
Right? So what that mean, like, okay, philosophically speaking, like, what are we doing here?
Okay. Okay. What we are doing here is we are assuming that we will always, okay. There is one more example I want to do, but which is pretty long. I'll upload this example, okay. The other, okay, just a minute. Right, okay. Oh, right. Okay.
Before you raise this part,
Oh.
I have another question about here. Like, it's Q, B, and L.
Yes, yes,
So B, and we make a left, right?
yes.
So why did you say terminal? Terminal state and zero.
Yes, actually, that's what I made a mistake here. Okay, so here your delta is simply -2, because if you take, okay, that part, the reward part is certain, right? You're in B, you take a left, you go to A, your reward is -2 plus gamma is 1. Okay, gamma is 1. Now again, when you are taking for A, you have to take max of A prime. You have to consider QAR, comma Q. Oh no, here it doesn't apply that way. Sorry? Yes, the next state is 0. State A. But you even have T there, right? Oh, right. Okay. Thank you. So, max of actions, yes. So, you're going to the left, the state is A. In that, you have two possible actions. So, you will write QAR, comma, QAL minus Q of BL, which is 0. Okay. Now, here, we have QAL as 0. Okay. QAR is 0 here. However, this is online learning. So we take the value that we got previously, right? So this would be 0.5. Yes. Sorry? Sorry? QAR, we calculated here, it's 0.5. Oh, delta, okay, right. So this one would be QAR would be QAR 0 plus 0.5 times 0.5, which is 0.25. Okay, so here this is 0.25. Okay, 0.25 comma 0. You know you have to take this value now. Why? Because you're using the max operator. Okay?
And why is it on
Online? Because we are using the update directly here. We are not
Why am I doing online?
because that's what the method follows here.
Oh, so Q-Learning is online.
TD learning online of policy. TD learning is online and Monte Carlo is online as well. Offline is something where you wait for the episode. Here, I wouldn't use 0.25 here if it was offline. I would use 0. But here, because it is online, I will use, whenever I get a new value, I directly use it. Okay? So this would then be -2 plus 0.25 minus 0, which would be minus 1.875. No, 1.75, right? Sorry, yes, 1.75, okay? 1.75.
Generally speaking, is TD online?
TD is online, yes.
So TD and Monte Carlo both are online.
Yes, so is SARSA and Q-Learning, natural extension, yes. Okay, so 1.75. Now QBL would be 0 plus 0.5 times minus 1.75, which would be what? 0.875 here. Okay, so here your value would be QBL would be 0.875. Okay, however, if you were using SARSA here, right, you would get a higher negative value. Why? Because you're not considering the maximum, you're considering the action that you would actually take. Okay, when you do that, you will get this value, the QBL here would be more negative. In the sense, it will be the effect of a bad reward is more pronounced in SARSA initially. Obviously, after infinite samples and iterations, everything will converge to the optimal one. But then SARSA is more conservative in this sense, because it will always assume that, okay, this action is bad, finish. Whereas QAR, okay, QAR I think it would be more pronounced. Why? Because here the next action is take left in B, which we know is a bad action because of the rewards, right? In SARSA, this value would be 0, which would mean QAR and this iteration would still be 0. However, it is 0.25, a better number, right? Why is it higher despite knowing that the next action is bad? Because we are assuming that we will take the best action when we go there, right? That is why we take this value, the higher of the two values. Clear? Yes.
So the only difference between all of the policy are just
Exactly, just this term, just this term. In fact, just this one term, right? Clear?
So we are basically greedy that way, irrespective of the policy, right?
Absolutely, yes, yes.
Which is good or bad?
It could be both. There is no definite answer here that this is good, this is bad. Right? Let me give you an example. Say you are learning on a real hardware. Okay, you have a robotic arm. You are learning on that. Okay, here in Q-Learning, because this action, okay, if it was, say it was SARSA, you know that this action would still get, this action value function would still be 0, implying that it's not very good. But here it will encourage the agent to take this because it's a good action, right? This state action QAR is still 0.25, right? This is 0.25. So this is still a good number, better than 0. Which is better among these two? This one, right? And here, so despite knowing that this policy will make you take a left in the next action, it will assume that no, that will not happen. We are assuming or preparing for the best case scenario, not the worst case scenario. We'll be like, even if the policy says, let it be, because when I go there, I will make sure that I'll take a better action, right? So when you are learning on, say, a real platform like a robotic arm, SARSA is better in that sense. Why? Because it's more conservative, right? Okay, I'm walking from here to there, okay? And there is a cliff here right beside me, okay? One bad action, I fall off the cliff, okay? In that kind of learning, SARSA will be like, no, walk further away from this goal, and then when you reach the goal, then like be more conservative while you're walking. Whereas Q-Learning will be like, no, you're the best you're the best runner, you will never fall in the pit. You will never take a wrong step. While learning, Q-Learning will teach me like that. Whereas SARSA will be like, no, be conservative. You will eventually reach there in the shortest time, but then let's explore a bit further away part. Don't walk from here. Whereas Q-Learning will be like, no, this is shorter. Go closer to the cliff. Go closer to the cliff. Right? So Q-Learning is more bold in that sense, whereas SARSA is more conservative. But eventually, obviously, both of them will converge to the same optimal policy. Okay? So from this, you might understand that yes, the samples that it would take for SARSA to learn, or the data that it would take for SARSA to learn, will be higher than Q-Learning, right? For this example, at least. Okay? Despite that being more conservative, we would prefer that at times. Why? Because it's safer when you are doing on hardware. However, say if you simply have a simulator where you know that it won't break. It will simply respawn and redo the episode. There you have no problem of worrying about damage to anything. It's simply a number that will reset, that's it. So there you can use Q-Learning to learn, right? Right?
So why am I assuming the maps or my policy in the first place? Like, do I need to assume the policy in the first place if I am following Q-Learning?
Yes.
Why? Like if I'm already maximizing, optimizing, like he said, in a way, this is like initially like if we go to policy iteration or value iteration, this is like
Value iteration.
Value iteration, yeah, because I am not assessing and then optimizing.
Okay. There, I didn't want to use that analogy for this reason, because there you had a model, so you didn't have to take that to see what reward you're getting. You could simply plug in the values.
Something triggered here. Yeah, probably.
Okay.
My phone just like got triggered. I'm not sure why.
Okay.
Yeah.
So yes, there you had a model, right? You didn't have to rely on this transitions, this reward values. Here, what happens is, why do you need a policy here? Because you don't know the model. You don't know that if you take this action, you will get this reward. You will take that action and then see what reward you're getting, right? That is why you have to have, here by policy, we simply mean a set of actions, right? So we need something to happen in order to get this feedback, right? And that is why we need some policy, but we will be updating greedily. So simply to take an action or execute an action in that environment to get a reward, because we don't know the reward model as well. What we are simply doing is we will basically, okay, assume you don't know what happens if you jump from a cliff. You will jump from a cliff and then you're like, oh, bad decision, right? However, if you know that if you jump, you will fall down, you will not do that because you already know it. But here you don't know that what will happen when you jump off the cliff. So you will execute the action and then you're assuming that you have infinite life. So you're like, okay, next time when I am near that cliff, I will not jump. I will move to the left or to the right or wherever, right? Yes.
So we can say that on policy, like prioritize exploration, and of course it prioritizes exploitation.
No, both don't actually. That's the reason why we use epsilon grady, right? Because see, you will simply follow this policy, which is a series of action that you already programmed. You're like right, left, right, left, right, left. Either case, right? So exploration exploitation is not solved or not done through that. That's why you use epsilon grady.
But here is, like, he has a point. Here is more exploitative, right?
But okay, exploitation.
Like you said yourself, greedy, right?
It is greedy, but not exploiting. In the sense, okay, what is exploiting exploration is when you're exploiting it, you simply mean that you will repeat taking a good action always. Here you're assuming that you will take a good action when you go there next time. You see the subtlety here? If, okay, I'll go slowly. If you take the same action, okay, if you take a greedy action again and again and again, say, okay, now after 2 epochs, I know that taking a assume for some reason this value is 0.15 and this value is 0.5, okay? Because of whatever calculations in the first iteration, I got the values like this, okay? Which we know as a matter of fact is not correct. Why? Because if we take left in AL and then we'll not go to B, we'll be stuck in A forever, okay? But we'll not get this way. But assuming because of some calculations in the initial, because of say maybe your initial values, you will get this value. Now if you're exploiting, what will happen is every episode you take, you will always choose this value. Why? Because you'll simply assume that no, this is the better action in A. So that is exploiting. Basically you're exploiting the goodness of that action. You don't even bother exploring the other option. Somebody might tell you, okay, like say suppose you go to a restaurant, okay? The same sandwich example that I used, like you go there for the first time, you eat a chicken shawarma. You will that place is probably more famous for its beef shawarma, okay? But you will, because you like the chicken shawarma, you will be eating chicken shawarma always. You will never bother exploring the other kind of shawarmas they have, despite that being the better one. So you're not exploring, you're simply exploiting what they first offered you, right? So this is exploration exploitation. If repeatedly you simply take one action, here you're assuming that, okay, next time when I go to that state, I will take the better of the 2 actions or better of n actions I have, right? Clear?
Quite honestly, it's within this step, you're being greedy and exploitative. Yeah, I see your point. I see your point, but yeah, this is smaller calculus, but at that level, you're greedier.
Yes, at that point you are greedier, absolutely, yes. But then you are not exploiting it. Exploiting it in the sense that you're not taking that action actually, right?
Right, yeah, like it's just like
Assumption that you will take that action there.
the future word, white.
Exactly, exactly. Okay, so yes.
Can I say that Q-Learning is as artificial because then SARSA regarding we are computing maximum interaction rather than following one.
Okay, if that is the case, then probably the number of samples that you have to take in SARSA will offset this max computation. So there is no general theory or rule here that this is more sample efficient, this is more computationally expensive. Yes, in few cases this might be more computationally expensive, but because of the lesser samples you need, the computational demand will be offset. Depends on the application. That's why I do not explicitly state that this is more, as a rule of thumb, that this is more, what do you say, computationally efficient. No, right? Okay, clear? Yes.
We are in a state we have several actions.
Sorry again.
We are in a state.
You're in a state.
Like 3 actions, 4 actions.
3, 4 actions.
Yeah, for sure we are going to have the reward values for these actions. But
Yes.
similar. Some of them.
Yes.
Values similar. At the first we have a random policy. What if we go for a similar value, a positive value, right? And then, in the next step, it will consider like what we have calculated before. It won't make sense the algorithm goes for a local minimum.
No. Your Q or your V for that matter, okay, in some sense, approximately, are equal to what? They are the expectation of the expected return, right? One is given state action, the other is given state. So in general, the value functions are the expectation of the returns. What does expectation mean?
But here, before we are taking the maximum, we are taking previously with hinted. I mean, if it's not updated, it will be 0.
Yes, let it be 0. But okay, let me complete that point. So when you are taking an expectation, what are you doing? You're taking an average of it. Average of the returns over infinite samples. So you will make sure that you have visited every state action pair infinity times. So when you do that, you will not be stuck in a local minima. Say in A, you have 4 actions, right, left, up, down, okay? In the first epoch, you take right. Maybe for the first 100 epochs, you will end up taking only right in A.
But if we take into account the, I don't know how to say, the convergence curve, the learning curve, if we have 2 similar values, we'll actually have some fake convergence.
No, I didn't get this point. Sorry, again.
I don't know how to say.
Stationary point. You mean the stationary point?
Yeah, it will have a stationary point, and then it will, if we discover this new stuff.
Oh,
we'll have a
okay. So you mean for a while you might have a stationary value, and then yes, that might happen.
Yeah.
That might happen. That's why.
So,
Okay, when does that happen? Because you have not ticked the infinity criteria here.
yeah, because we are sampling, we are assuming that we take enough samples, we will converge to the right
Optimal value, yes.
So how do you discover this?
How do you discover the optimal samples you
How
mean?
to avoid this?
You simply run it for a very, very long time. Right? Because there is, like the neural network parameters, say the number of neurons, number of layers, even the number of episodes is a hyperparameter. The number of steps per episode is a hyperparameter. You let it run for as long as you can to get the best results. Okay? But you will see that this, so you mean a learning curve of this kind, right?
Yeah. Yeah.
Right? This is not very common, honestly. This will not happen. Like, it will not converge to this for a very long time. Yes, for a few episodes, for a few hundred episodes, it might. But it will be something, and it will not be this change. That's what, like, the variance will not be this high. You will see it changing. It will be like,
Should be advisable to say, in this case, we have, should be advisable to test the system with different reward engineering, reward function design.
sorry, again.
I understand that in these problems it's a very important step to design the reward function.
Yes.
So we can try with different reward functions in this kind of, in order to avoid.
Oh, absolutely, yes. Different reward functions, yes. Basically, you do an ablation over different reward functions, different neural networks, different algorithms, even for that matter.
Let's say a reward function has different objectives and so has some weights we take for which different weights. This can help.
That will help. That's why you can simply change the weighting of different, different tasks in the reward function. So basically, a reward function would be a conjunction of different tasks that you have put together, weighted differently, right? So you can change the weights and see how your performance changes. You get me? So again, that is something that you trial and error learning. Reinforcement learning by itself is trial and error learning, and the parameters of RL are also trial and error learning. Right?
Okay.
Clear? Yes.
You get a higher reward, but the objective is worse. This means the design of the reward function with the weights given to each one is that.
Yes. Yes.
So
Because
this might happen when I mess up the reward function.
absolutely. Why? Because your reward function is something that you formulate based on an idea that you want to achieve. You're like, okay, fine. If I complete this, my reward function ideally should do this things, right? However, that might not be the case how the agent is learning, right? Therefore, you might get a high reward and your task might not be completed. That is why you try to keep your reward function as simple as possible and try avoiding having contradictory terms, right? Because at times you might think that, okay, fine, no, I'll give, say, minus w1 x1 and x being some term in the reward. But later on in your reward function, you have, say, into x1. So now the RL agent will try to reduce and increase at the same time, which isn't a good thing for optimization, right? So you design a simpler reward function with preferably avoiding contradictory terms. Okay, clear?
Contradicting the word what again?
In the sense, say, I'll write a very rough example here. And you have some other terms. Okay, no, this is x1 again. Okay, say you design a reward function where here you have x1 minus x1 in the sense that you're trying to reduce this term. However, here x1 is positive, so you're trying to reduce x2. But simply because your weight or coefficients are different here, which could be anything, you think that, oh no, this reward function will achieve what I want to do. But no, it will be difficult. Even if this weights are not simply weights and they are complex coefficients, or not, I don't mean complex numbers, but they are more, they're coefficients with different terms, then you think that, no, if I formulate my reward function this way, the agent will learn better, but no. Right? And again, not a rule that it will not work. Right? However, if you start simple, it will be easy to debug and build on it. Clear? Clear? Okay. So yes, the first point addresses your query that yes, we assume that we visit all state action pair infinite times. Okay? Yes. Yes, this is the cliff walking example that I was talking about. SARSA is more tries to learn in a more safer way, whereas Q-Learning will be more bold in learning that. Okay, so that's that for Q-Learning.